Hi everyone, in today's video we are talking about inverse functions. In this video you are going to learn how to apply the definition of inverse to create an inverse function. We are going to use domain restrictions to ensure that inverse equations are also functions, and we are going to verify that two functions, when you're given two, are inverses, or disprove that they are not inverses. And then last, we're going to apply the horizontal line test so that if you have a graph of a function, you can use just that graph to tell both whether the function isn't if the function is a function, and also if the inverse of that graph is a function. So let's get started. The first thing that we need to look at is, remember from Unit 2, this was at the very beginning of the year, we talked about inverse functions then. They are functions that map output values back to their original input values by interchanging the input and output values from the original function. Remember, this is when we swapped the x and y, the placement there. And it also interchanges the domain and range. The x's and y's of the domain and range flip when you look at an original equation versus the inverse equation. So let's look at two graphs, two equations, and look at their relationship, which is an inverse relationship. So this first function, f of x is equal to x squared, where x is greater than or equal to 0. This is just a parabola because this is x squared. There's nothing fancy going on. The origin's going to be at 0, 0 because there's no h and k values, and there's no a value out front, so it's going to be standard, just like the parent. So looking at that, 0, when we plug in 0 squared there, we're going to get 0. 1 means that 1 squared is going to be 1. 2, when we input that, 2 squared is 4. And 3, when we input that, 3 squared is 9. So now if we graph this in red, we've got 0, 0, 1, 1, 2, 4, and 3, 9. So we get a graph that looks like that for f of x. Now, when we do g of x is the square root of x. And I'd like to take this one and plug it into the calculator so that we can see what this looks like, because some interesting things are going to happen. So in the y equals, I'm going to put in the square root of x, and then I'm going to look at it in the table. So I'm going to hit second graph instead of just graph. So according to this table I have on my notes sheet, I need to look at where x is -1. And if we look there at where x is -1, do you see how you have an error message, and you have an error message for everything above that, or all x values that are lower than that? That is happening because if we look at the graph, our function starts at 0, 0 and then goes to the right to positive infinity where the x's are. So there's no graph over here on the negative side of the x-axis, which means you're going to get error messages for all of these values because there's nothing there. So going back to my table now, at 0, I have 0, 0. Oops. At 1, I have 1, 1. At 4, I have 4, 2, and if I scroll all the way down to get to 9, I have 9, 3. So looking at that graph, and I'm actually going to change my color for this one to blue. Sorry, I forgot to change it earlier. I'm going to do 0, 1, 2, and 3 for this one. 0, 0 is still the origin. 1, 1 is still that point, but then I go over 4 and up 2, over 9 and up 3. So I get this graph here. Notice that this is the flipped or inverse of the red graph f of x that we just drew. Notice that when you look at these two tables, 0, 0 flipped to be 0, 0, 1, 1 flipped to be 1, 1, 2, 4 became 4, 2, and 3, 9 became 9, 3. So we have inverses here. And you may also remember from earlier in the year, when you're looking at inverses, there is a line of reflection. This is the line that these two graphs flip over to get the other one. So when you take f of x and flip it over this line, y is equal to x, it gives you g of x, the inverse function. Okay, so now let's look at the way to do this algebraically, not just in the calculator. You may recall that in order to find an inverse relation and solve it, we are going to flip the x and y, and then we're going to solve it for y. So in this first example, y is equal to 4x plus 2. When I create my inverse, I am going to flip the x and y. So I'm going to put x is equal to 4y plus 2. So I've just swapped those two variables. Now I'm going to solve for y to get my new equation, my inverse equation. So I'm going to subtract 2 from both sides, and then I need to divide by 4 on both sides. I'm also going to write this as y is equal to rather than the other way. So y is equal to x minus 2 divided by 4. And this is my inverse equation because it flips the x's and then the y's. So let's look at another example. Let's find the inverse relation for the equation and then also figure out the domain and range for both. I'd like to do the domain and range for the original function before I do anything else. Now, if you want to do this with a calculator, you can graph this in the y equals and then figure out your domain and range by looking at the picture. Where's what's the interval for the domain, what's the interval for the range. Now, you also can think about this in terms of input and exput values. So if you ask yourself, what inputs, what x's can I put here? You could put any real number there and simplify this equation, and it would tell you what y is equal to. So because I can put in -5, -4, -3, -2, 0, 1, 2, 8, 1,000, any real number can go in there. The domain is going to be all real numbers. And the output value, the y value that I get out, it's also going to be a real number. If we're thinking about the graph of this, because this is a cubic, that means it's going to be that squiggly shape. And that also, that graph has a domain and range of all real numbers in both cases. So let's actually find the inverse relation for this one now. So the first thing that I'm going to do is I'm going to flip the spots for my x and y. I'm going to swap those. So I'm going to say x is equal to 1/2 y to the third power minus 2. Now I need to add 2 to both sides first if I'm solving for y. So that gives me x plus 2 is equal to 1/2 y to the third power. And then I need to multiply both sides by 2 because that will get rid of this 1/2. So that gives me y to the third is equal to 2 times x plus 2. And then I'm going to go ahead and distribute this 2 into that factor. Y to the third is equal to 2x plus 4. And then in order to get rid of this cube, because I want my equation to just be y is equal to something, I'm going to take the cube root of both sides because I have a triplet or 3 y's. And if I take the cube root of it, that triplet of y's, those 3 y's, will come to the outside. Cube root of y to the third is just y. And that leaves me with y is equal to the cube root of 2x plus 4. And that is my new relations equation. Now remember, because the x and the y, we flipped them originally, that means the domain and range just flip. So whatever you wrote for the range of the original, you're going to write that as the domain of the inverse. And whatever you wrote for the domain of the original, you're going to write that for the range of the inverse. Now in this case, those are both just all real numbers. There's not much exciting going on. That will not, however, always be the case. The next thing that we need to talk about is how to verify whether or not equations or functions are inverses of one another. And we have this idea that if you have two functions that are inverses, then we can look at composition. F of g of x, when you compose g of x inside of f, it's going to equal just x, whatever the input value is. And the opposite is also true. G of f of x is equal to x. This is a way of proving or verifying that two functions are inverses. If you compose the two functions together as f of g of x and also g of f of x, they both have to equal x. And if that's the case, then you can say that the two functions are inverses. I also want to point out just very quickly that there is a notation that you're going to encounter that you need to be familiar with. This f to the negative 1 power, that's read as f inverse. So if I have a function f of x and I find the inverse or compose two functions to see if the inverse is if it is the inverse, you may see this written as f to the negative 1, which is read as f inverse. That new function, like we were just creating on the previous slide, is called f inverse, or the inverse of the original function. So let's do some application with this idea about verifying functions. So we want to verify that f of x and g of x are inverses of each other. So we're going to do the composition both ways and then state what we know. So first we're going to find f composed with g of x. That means we're going to take g of x and substitute it in where the x is in f. So I'm going to do 4 times something plus 2, but where that x normally is, I'm going to insert all of g of x. That's 1/4 x minus 1/2. So let's see, let's take this 4 that's being multiplied and distribute it. So that gives you 4/4 times x minus 4/2. And then you've got that plus 2 on the end. 4/4 is just 1, so that's x, and 4 divided by 2 is 2, so that's x minus 2, and then there's that plus 2. Negative 2 plus 2 is 0, so this is equal to just x. That first part worked with the rule that we just talked about. I composed f of g of x and I got just x is what it was equal to. So now let's do it the other way. Let's do g of f of x and see if we get that it's equal to x as well. G of f of x means we're taking f of x and putting it inside of g. So I've got 1/4, and then I'm going to leave some space with parentheses there, and that minus 1/2. I'm going to take f of x, which is this guy, and put him where that x spot is. For this one, I'm going to distribute the 1/4, so that's 4 times 1/4, which is just 4/4, or 1, and that's 2/4, minus 1/2. 4/4, as I just said, is 1, so that's x. 2 divided by 4 is 1/2, and then I have that minus 1/2. Positive 1/2 minus 1/2 is equal to 0, so that gives me that it's just equal to x. That means this one also checked, it verified. So now we can state the equivalency. We can say f of g of x, that's the first composition we did, is equal to g of f of x, that's the second composition that we did, and both of those things are equal to x. This line will always be the same, though the two names of the functions might change. If it's called something besides f or g, then you would use those letters there. But otherwise, this final statement of equivalency will always be the same. All right, so second to last big idea that we need to talk about is that if you have two functions that you need to decide if they are inverses of one another. So when you're looking at graphs of power functions, if you have f of x, which is x squared, and g of x is x to the third, and we reflect them over this line, then you need to be thinking about, well, that new equation, is it a function? Is it 1-to-1, or is it not a function anymore? So if we look at this first one, the x squared graph, do you see here how when we flipped this, it turned on its side like this, and this is no longer a function because it doesn't pass the vertical line test. This red guy is not a function. The only way to make it a function is to restrict the domain so that it's only non-negative real numbers. Because if we're looking at non-negative real numbers, then we're only looking on the original at the right-hand side. We're looking at this part here. And when it flips, we are only looking at this part here, and that passes the vertical line test. So in order for the equation f of x is equal to x squared, for the inverse to be a function, you have to restrict the domain to be only half of the parabola. Now, with the cubic function, In blue here, you've got the original cubic function. When it got flipped to be the inverse, notice that this inverse, this red line, passes the vertical line test, which means it's also a function. It's one-to-one. It's only the quadratics, the ones that when we flip, we fail the vertical line test, that we have to restrict. Now, before we do this last example, I do want to give you a secret message for today. I would like for you on this same section of your notes sheet where we've talked about determining if an inverse is a function to draw a flower up in this top right corner. It doesn't have to be a super fancy flower. Just draw me a flower so that I know that you're listening to today's video. Okay, let's look at this example where it says find the inverses of f of x, knowing that x is less than or equal to 0, and then graph both f and f inverse, the inverse function. So let's see, if we want to find the inverse using algebra, then we are first going to need to write this equation and flip the x's and y's. So I'm going to write this exactly as it is, just instead of f of x, I'm going to put a y there. This is my original function, the one that I'm graphing. So let's go ahead and graph this. hk in this function is 0, 2, and a is just equal to 1. So that means this parabola is going to have a vertex at 0, 2, and then it's going to be just like the parent. So when we go over 2, we're going to go up 1, 2, 3, 4. Now, I just made a small mistake here. Do you see what I did? This restriction said that x has to be less than or equal to 0. So I'm drawing the whole parabola here, but really I should only be drawing the x is less than or equal to 0 side. So that's the left-hand side. So I'm going to erase a couple of these ordered pairs because I don't need them with that restriction. That guy's going to go away and that guy's going to go away. If x is less than or equal to 0, then that means I'm only looking at the left-hand side of the graph. Now, knowing that, that means your domain is from negative infinity up to 0 because x is less than or equal to 0. The range, on the other hand, is going to be from 2 up to positive infinity. So that is y is equal to, oh goodness, that is y is, greater than or equal to 2 because it rises up from there. Okay, so now that I've got all the stuff relating to the original function done, let's go back to the problem and find the inverse. I'm going to change my color here because now I'm going to swap my x and my y. All I've done is switch the position of the x and the y. Those two variables, I flipped them around. Now I'm going to solve this for y because that will give me my new function or my new equation. So I'm going to subtract 2 from both sides first, and then I'm going to take the square root of both sides to get rid of that square. So I've got y is equal to plus or minus the square root of x minus 2. Now we do need to make a choice here. Because of this domain restriction, we are going to choose only one of these, the plus or the minus, not both, because we're only graphing half of the parabola, remember? So for this one, because this is x is less than or equal to 0, that less than or equal to sign means that we are going to restrict the domain by the negative side because it is less than, smaller than. So for my final answer here, my restriction is going to be negative square root of x minus 2. So when I choose that, this is going to only give me half of the parabola flipped on its side. And if I rewrite this using f inverse notation, which is what the problem originally said, I'm going to say f inverse of x is equal to negative square root of x minus 2. So that's my equation there. So going through this real quick, I took my problem, I flipped the x and y, then I solved for y, and then depending on what the domain restrictions are for the original problem, If that is a less than or equal to sign, you're going to pick the negative side for your square root. And if it was a greater than side, you would want the bigger side, the large side of x's, so I would have picked positive. And then I just rewrote, instead of y is equal to, f inverse of x is equal to. So let's think about this now. This is a square root function where hk is at 2, 0, and the a value is -1, which means it's going to flip over to be the bottom side. So I'm going to plot 2, 0, and then instead of graphing it up here like that, I'm not going to graph that side, I'm going to graph the negative side. So I'm going to do this bottom half. When I go down 1 squared is 1, so I'm going to go over 1. Then I'm going to go down 2 and over 1, 2, 3, 4. And that gives me my square root function there. So notice that we took this line of reflection and flipped it over. The domain of f inverse is going to be x is greater than or equal to 2, because it's 2 to positive infinity. And the range is going to be that y is less than or equal to 0, because it's negative infinity up to 0. Now notice here that my domain of my original function f, that moved to be my range. I changed the x for a y because those flipped, and my range became my domain, though I changed my y to be an x because we changed those places in the original flip that we did up here. All right, the last piece of the notes here is the horizontal line test. And technically, this is just a reminder. We did this at the very, very beginning of the year in Chapter 2. So we talked about the vertical line test and the horizontal line test at the beginning of the year. The vertical line test said if you had a graph and you could take a vertical line and move it across the graph from left to right, and you only ever touched the graph at one point at a time, then it passed the vertical line test, and so this was a function. So what we're going to do is we're going to use the horizontal line test for inverses. If you're looking at an original graph, like this one here, I haven't flipped anything, and you can look at that graph and do the horizontal line test, going horizontally across the graph, and it only touches at one point, no matter where you put that horizontal line, then you can say that the inverse is a function without having to do all of the work that we've done in this section so far. Now, the inverse is not going to be a function if it fails the horizontal line test, meaning that the horizontal line touches the function in two places. So when you look at the original function, if a horizontal line touches it in two or more places, then that means the inverse, when we flip it, is not going to be a function. It's going to fail. So the function can be called, well, the graph can be called one-to-one if it passes the horizontal line test, meaning that it is a function. If it fails the horizontal line test, it is not a one-to-one function. All right, so in this video, we applied the definition of inverse to create inverse functions. That's where we flipped the x and y and then solved for y. We used domain restrictions to ensure inverse equations are functions. We chose whether to use the plus or minus in example number 4 to do that. And we verified that two functions are inverses by using composition. We did f of g of x is equal to g of f of x. If those both equal x, then they were inverses. And then in the last part, we used the horizontal line test to look at a graph and say whether the inverse was or was not a function. Go ahead and try the Now You Try now.